My name is Henry Corrigan-Gibbs, and I'm going to present some joint work with David Walensky and Brian Ford about our anonymity system called Verdict. So to start out, I want to tell you a story about a particular country X that's about to have an election tomorrow. And on the eve of this election, an activist learns that the prime minister has been stashing some stolen money in a bank account. So the activist gets a hold of these account numbers and wants to publish these before the election. At the same time, the activist doesn't really want to publish these numbers under his own name for fear of harassment or arrest. So he wonders if he can publish them anonymously. His first idea is to post these account numbers to a blog over an onion routing system. But he's worried that the state-owned ISP might be able to function sort of like a global adversary and perform some sort of first-last correlation attack on his traffic. So the activist gets another idea. Instead of using onion routing, he'll try to use an anonymity system that's resistant to traffic analysis attacks, like dining cryptographers' networks. So for those of you who don't know about DC nets, basically the way they work is the activists would need to gather a group of people, potentially his friends or other activists. They would all run some protocol in which they contribute an equal length message, and at the end of this protocol, the account number would pop out, but no one, an outsider or even an insider, couldn't tell which one of the group members was actually the anonymous transmitter here. Then the account number could be posted to the blog server. So to give you a little bit more background on DC nets, I just want to quickly run through how they work. It's an anonymous broadcast primitive, so there's a group of participants, all of whom know each other, and they all share secrets with each other. So here the secrets are just single bits. And one of these group members has an anonymous message that she wants to send. So here Alice's message is just a single bit. So to send this message, each group member will take the XOR of their shared secrets, and that will be the transmission that they send in this DC Nets broadcast round. And Alice takes the XOR of her shared secrets plus her message. So each of them ends up with this XORed bit. They all broadcast their bits and then XOR them together, revealing this single bit message that Alice sent. But notice that DC Nets are resistant to traffic analysis attacks because everyone has sent an equal length message, so they've all sent the same number of bits, and all of their bits are XORed with these shared random secrets. So from an outsider's perspective, or even a group member's perspective, all of these messages look random. So a system called Dissent we've been working on for some years tries to make DC Nets practical. And it does this by splitting nodes into clients and servers so that we can scale up to thousands of clients. We can also handle client churn, so clients who come and go. And the anonymity set size that's provided is equal to the set of all honest nodes. So back to our activist. He realizes that DC Nets resist traffic analysis attacks, but he's worried about what might happen if the prime minister's henchmen can infiltrate this group. So say a number of these activists are actually the prime minister's henchmen. To see why this is a problem in DC Net style systems, we can go back to this diagram and see that if, say, Chris is actually an adversary, he might not send the bit he's supposed to send according to the protocol. He might flip his bit at random, which would cause a corruption in the output of the protocol. And this is sort of like a denial of service attack that's also anonymous, since Alice can't tell whether it was Chris or Bob who corrupted the message. So the Dissent system I just mentioned can handle this sort of misbehavior. And the way it does this is after disruption occurs, participants run a shuffle or an e-voting protocol in which the anonymous sender submits an accusation through the shuffle, which participants can then use to figure out who is the disruptor. The problem in Dissent, though, is that this takes some time. So in a network of 1,000 nodes, this blame process can take over 20 minutes, which leads to a different attack on the anonymity system. So if the henchmen, again, can control some fraction of these nodes, they can DOS the protocol just by sacrificing themselves one at a time. So one of the henchmen corrupts the transmission, then will be identified by this blame protocol and kicked out, and this will continue. But the problem is that the henchmen can potentially block the activist transmission until the election has passed. So just by delaying protocol progress for long enough, the henchmen can essentially win the game. And to see why this is bad, well, in a 1,000-node group, just 18 disruptors can block communication in Dissent for 6 hours. So if the disruptors can control more like 10% of the nodes, they could block communication for a day or more. So this is the motivation for Verdict, which is a system built on top of Dissent. We're trying to get the traffic analysis resistant properties of DC Nets and the scalability of Dissent, but with a much lower blame cost. And the fundamental idea we use is that group members prove that the messages that they're sending are properly formed so that we can identify disruptors before they're allowed to jam the anonymous communication channel. So the most closely related work to this was the 2004 Eurocrypt paper by Goulet and Jules, in which they propose using zero-knowledge proof techniques on top of DC nets. And they have participants prove in zero knowledge that their messages are correctly formed as they're being sent into the DC net. The drawbacks of this work, though, is that it's computationally expensive, the construction they describe. It's inefficient in terms of communication cost. It uses pairings, which requires non-standard cryptographic assumptions, and requires trusted setup. It's also never been implemented or experimentally evaluated. So with Verdict, we provide the first, to our knowledge, implementation and evaluation of verifiable DC nets. We give 2 new verifiable DC net constructions, which give nearly a 6x speedup over the closest related work. And we give a number of optimizations to make verifiable DC nets fast, when message sizes are long, when there's no active disruptors in the group, and by optimistically using XOR-based DC nets when we can, which gives nearly 140x speedup over the prior work. So this is the outline for the rest of my talk. I've just described some of the background and motivation. I'm going to talk now about Verdict's design challenges that we had to overcome, a number of optimizations we make to the system to make it fast, and I'll conclude with our evaluation results. So the first design challenge I want to talk about is how we get resistance to traffic analysis attacks. So the way we do it is by dividing time into messaging rounds in Verdict, such that there's only one anonymous sender in each messaging round. And the key ideas for traffic analysis resistance are that every client must transmit the same number of bits in every messaging round, so that the number of bits you're sending doesn't leak whether you're the sender or not. The other important property is that client ciphertexts have to be cryptographically indistinguishable, so that the content you're sending also doesn't leak whether or not you're the sender. So this is graphically how it works. We have the network partitioned into some servers, into some clients, as in descent. And we make the additional assumption on top of the cryptographic assumptions we make that there's at least one honest server in the network, though the clients don't need to know which one of the servers is honest, as long as one is. So in each messaging round, the clients generate some ciphertext message. We'll explain how we do that later. The clients then submit the ciphertext to the servers, or their upstream server. The servers then exchange some messages between themselves, and at the end of this message exchange, the servers are able to recover the client's plain text, or the anonymous sender's plain text, which they then return to the clients. So again, the key idea here is that we've divided time into messaging rounds, and we require every client to send the same number of bits in every messaging round, and these bits that they're sending have to be cryptographically indistinguishable. So how do we do that? How do we make the sender's transmissions indistinguishable so that we can't tell who's the author or who's the anonymous sender and who's just a regular client? So this is the second challenge. How do we encode these messages? The basic idea is that we have the transmitting client send the encryption of an arbitrary message with a special encryption scheme, and we have non-transmitting clients encrypt a message where m equals 1, so an encryption of the identity element. And we use an ElGamal-like scheme. It's not exactly ElGamal, but we use an ElGamal-like scheme to encrypt these messages. So just to give a graphical depiction of that, we have these clients and servers again, and the dashed lines indicate the secret sharing relationships between the clients and the servers. So each client shares a secret with each one of the servers, and these secrets are agreed to using a Diffie-Hellman key exchange. So to generate her ciphertext for messaging round T, Alice takes some generator G sub T and raises it to the power of her 2 shared secrets added together. Bob does a similar thing, and Chris does a similar thing, except that his ciphertext is generated by taking G sub T, raising it to these 2 powers like Alice did, except he multiplies in his plain text message. The servers do the similar thing, except they have 3 shared secrets, 1 for each client, and they flip the exponents on their shared secrets. So I'm not going to put the math up here because it was going to take too much space on the slide, but I think you'll trust me if I say that in the product of all of these ciphertexts, each secret is included with a positive sign and an exponent once, and with a negative sign and the exponent once, so that if you take the product of all of these things, all of the shared secrets cancel out, and you're just left with this plain text message M. The other thing I want to point out is that if you don't know all of the shared secrets, all of these sigma values in the exponents, you can't tell whether Alice or Chris is the one sending this message M. And that's because, from your perspective, if you don't know, say, one of these shared secrets, the ciphertext element has just been multiplied by a random value, or random group element, I should say. Okay, so this brings us to the last design challenge in Verdict, which is how do we prove that these transmissions are well formed so we get the disruption resistance that we want? The first step to doing this is having clients attach non-interactive zero-knowledge proofs of knowledge to their ciphertexts. And we can do this with just standard off-the-shelf zero-knowledge proof techniques. So when clients, in each messaging round, clients generate their ciphertext, they generate this proof of knowledge, and they send the ciphertext element along with the proof up to the servers. The servers then check these proofs, generate their own ciphertext elements and their own proofs, and then the servers exchange these proofs within themselves. So we can detect both client and server misbehavior. There's one more thing I need to mention about this before I show the proof construction, and that's, remember that I mentioned that one client transmits in each messaging round. So there's only one anonymous sender in each messaging round. So we need some way of figuring out who's going to transmit when, who's going to own which messaging round. And we do this in Verdict in a similar way to how it's done in Dissent. We use a key shuffle to assign pseudonymous owners to messaging rounds. So how that works is that each client, in a setup phase before the messaging rounds begin, each client generates a pseudonym public key pair, or pseudonym key pair, and submits the public key to this secret key shuffle. The shuffle protocol, which the servers run, spits out some permutation of the keys such that no one knows the entire permutation. So Alice, in this case, owns pseudonym F, but Alice is the only one that knows that she's the owner of that key. So the important thing to take away from this is that there's a pseudonym public key assigned to each messaging round in Verdict, and everyone knows which key belongs to which round. So how do we use this in the proof of correctness? Well, when Bob submits a ciphertext in a messaging round owned by a particular pseudonym, here pseudonym D, Bob attaches a proof of knowledge that C Bob is either a correct encryption of M equals 1, which means that C Bob is a correct non-transmitter ciphertext for that messaging round, or Bob submits a proof that he knows the pseudonym secret D. So in that case, Bob is actually the transmitter for this messaging round. And the important thing is that the verifier of this proof can't tell which of these two branches of the OR statement Bob has satisfied. So there's one more piece that we need before I show the proof construction, which is that clients and servers also have to publish commitments to their shared secrets. And we do this just by taking some generator H and raising the shared secret to, raising H to the power of that shared secret. So again, in a session setup before the messaging rounds start, everyone publishes commitments to all of their shared secrets. So here, each server has 3 shared secrets, so they each publish 3 commitments, and each client has 2 shared secrets, so they each publish 2 commitments. Okay, so this is again the proof statement. I'm now going to show the symbols, but don't be scared. You don't actually have to know this notation. It's not important unless you're interested in the details of how it works. But basically, the elements I've highlighted in blue are all of the public things. So everyone knows what CBOB is. These big S's are the commitments to the shared secrets. The big D is the pseudonym public key for this messaging round. And then these generators on the right are just public generators that everyone knows. So if Bob is not transmitting in this messaging round, Bob will know the shared secrets, the secrets that he shares with each of the servers. So he'll know these secret exponents on the right, and he'll be able to satisfy the first branch of this OR statement. On the other hand, if Bob is the owner of this messaging round and he's transmitting a secret message, he'll know the pseudonym owner's secret key. So he'll be able to send whatever he wants in that messaging round, and he'll be able to satisfy the second branch of this OR statement. So for the people who haven't seen this before, the proof that's generated from this is just a bit string that you can send over the network. So how do we put that all together? We have in each messaging round, the clients generate these ciphertext elements using the construction that I just talked about. They each attach a proof of knowledge to this ciphertext. They all send these proofs up to the servers. The servers check the proofs, then generate their own proofs in ciphertext and exchange those. And if all the proofs verify and are correct, the ciphertexts can be combined in the way I described to produce this plain text message M, which is then sent back to the clients. And this repeats for the next messaging round and the next one. Okay, so that was the basic design of Verdict. I'm now going to talk about a few optimizations that we've used to make this go faster. So the first is how we deal with long messages. The naive way to do long messages is to have one proof for every ciphertext element that you're sending. But if the plain text message spans many ciphertext elements, it's a long message, that would involve having a bunch of proofs, so one proof per ciphertext element. It turns out that we can actually do much better than that. You can't see the grayed out stuff there, but basically, this proof is the same as before, except we've added a bunch of branches to the AND statement. So for each ciphertext element in this long message, we add an AND branch in the statement. And I'll just note that the generators are the only things that are changing here, and we just use a public hash function to pick the generators. But the nice thing about this construction is that the proof length is actually linear in the number of variables, but there's only a constant number of variables here. So the proof itself is constant length, no matter how many ciphertext elements we're going to prove correctness of. So that enables us to get short proofs even if the messages are very long. The second optimization I'll talk about is lazy proof verification. So checking these cryptographic proofs of knowledge is somewhat expensive. It requires big integer exponentiations if you're using integer groups, or requires elliptic curve operations if you're using elliptic curve groups. So we don't want to check these proofs if we don't have to. What we can do instead is have the servers defer checking the proofs until after a disruption has occurred. So all we need to do is figure out some way to get the servers to identify when a disruption has occurred, and then we can tell them to not check the proofs until after that's happened. So the way we identify when a disruption has occurred is by having the anonymous sender sign the content that she wants to send with her pseudonym secret key, and then she embeds the signature and the content inside of this plain text M. So when the servers at the end of the messaging round reveal this plain text M, they parse M into a signature and content, and then check if the signature is correct. If the signature is okay, the servers don't have to verify the proofs. The servers only go back to look at the proofs if M, the signature on this content is invalid, and then they check the proofs just to see who's to blame. The last optimization I want to talk about is a hybrid dissent plus verdict DCNet. So verdict relies on a lot of public key cryptographic operations. So basically everything you do requires public key cryptography. Whereas dissent and traditional DCNets rely on symmetric key crypto and XORs. So we would really like to use dissent most of the time and only use verdict when we really need to. So how we do this is remember that after a disruption in dissent, the anonymous sender broadcasts this accusation using a verifiable shuffle protocol. And the participants then can take this accusation and use it to figure out who is to blame. Well, it turns out that over 99% of the blame process is spent doing this shuffle protocol. So if we can somehow get rid of the shuffle protocol, we can make this all go much faster. So the basic idea here is to use verdict instead of a verifiable shuffle to broadcast dissent's anonymous accusation. So to see how that works in practice, here's sort of a diagram of what's going on. When participants set up a dissent DCNet session, they also set up a verdict DCNet session at the same time. So when things are going well, when there's no disruptors, participants all transmit their messages using the dissent DCNet session. As soon as the disruption occurs, participants switch over to using the verdict session, and the anonymous sender whose slot was corrupted or whose messaging round was corrupted submits an accusation through the verdict DCNet. So once participants receive this accusation, they can identify and kick out the disruptor, and then they return to transmitting in dissent. So the bottom line here is that by combining these two DCNet constructions, we can get the speed of a dissent XOR-based DCNet in the normal case, and we only have to use verdict, which uses a lot of public key crypto, under disruption. At the same time, when we do switch over to using verdict, it's much faster than these verifiable shuffles that we would have to use otherwise. Okay, so now I'm going to talk about our implementation and evaluation. We implemented all of this in C++ as an extension to dissent, and we used a variety of crypto libraries to test it out. Most of the groups that we use, actually all of the groups that we use in the slides that I'll show here are elliptic curve groups. And for our macro benchmarks, we used the DeterLab testbed with up to 128 client machines. And then we ran multiple client processes on each machine to simulate networks of up to 1,000 clients. And our source code is all online if you're curious. So this first slide shows the encryption throughput for each of the different schemes. So you'll notice the top line here, or actually I'll start with the bottom line. So this is the pairing-based variant of the proof construction. So this is the one that's closest to the Goley and Joules scheme that I mentioned from 2004. I didn't present the pairing-based construction here, but that construction is described in the paper. So the pairing-based scheme, the maximum throughput that you can get on a modern workstation is about 4 kilobytes per second in terms of just encrypting messages. The ElGamal variant, which again is described in the paper but I didn't talk about here, gives a 3x speedup over that prior work. And then the fastest verdict variant, which is the one that I described here, gives almost a 6x speedup. The hybrid DCNet, since again it uses mostly symmetric key crypto, gives almost 140x speedup over the related work, mostly because it only uses this public key crypto operations when it needs to resolve a disruption. This chart shows the messaging latency for tweet length messages in a variety of network sizes. So the most interesting numbers are on the far right. So in the largest network size we tested, which is 1,024 nodes, the pure verdict DCNet has messaging latencies of around 34 seconds. The lazy verdict optimization, which I described just now, gives around a 2x speedup over pure verdict. Again, that's because we only check the proofs if there's a disruption, so we don't have to check the proofs every time. And then the hybrid DCNet, which uses this XOR-based, more traditional DCNet approach, in the normal case, gives a 27x speedup. This last graph shows the time it takes to identify a disruptor across different network sizes. So you can see here, this is a log plot, by the way, that descent takes far longer than any of the verdict approaches. So identifying a disruptor in a descent DCNet takes around 1,200 seconds. And again, most of that time is spent running this verifiable shuffle protocol. The hybrid DCNet takes only 24 seconds to identify a disruptor in a network of 1,000 nodes. And the pure verdict DCNet takes only 6 seconds to identify a disruptor. So again, we've reduced the cost of identifying a disruptor in a 1,000-node DCNet from 1,200 seconds to 6 seconds. Okay. So just before I conclude, I want to mention again that there's a lot of details in the paper that I didn't have time to talk about, so you're welcome to ask me about them after the talk or refer to the paper. So to conclude, we've described the first practical verifiable DCNet scheme, and we've presented 2 new DCNet constructions, both of which use these verifiable techniques to achieve disruption resistance at a much lower cost. We've reduced the cost of finding DCNet disruptors by around 2 orders of magnitude. And by reducing the cost of disruption, Verdict aims to bring traffic analysis resistant anonymity at least a few steps closer towards practicality. So I'd just like to finish by thanking all of these people who helped give comments on the paper and helped us with our evaluations. There's our website. And Brian required me to say that the Descent project is hiring. So if you're interested, please talk to me afterwards. Thanks.
So you're using a provable shuffle. Hello. Yes. So you seem to be using a provable shuffle, and you build upon that to allocate the slots for descent. So what I'm a bit unclear about is if you already are using a provable shuffle, which is an anonymity system, why do you then use descent? Why don't you just use that in order to also relay the messages, I guess?
Sure. So the answer is, let's see, in this, make it go away, in this slide. So just for sending a short message in a provable shuffle requires 1,200 seconds, whereas sending the same message through Verdict requires 1 second. So that's the reason why we use the Verdict system. So we could certainly use a provable shuffle for everything. It's just that we get much better efficiency when the messages are of different lengths, or actually we get much better efficiency when we're running this multiple times than we would if we sent everything through a verifiable shuffle.
I actually have a related question. So you're using the provable shuffle to assign clients to slots. Does it really have to be a full-on shuffle, or could just a rotation do, a provable rotation, which should be much easier?
So a provable rotation, meaning you'd start with Alice, Bob, and Chris, and then you would slide.
You like sort their public keys in numerical order or something.
Sure.
And then do a random rotation of that, and then assign slots that way.
So you're saying you do a shuffle once and then go through that rotation many times?
Not even a shuffle, though.
Or you do a rotation once, or a sorting network or something?
Yeah.
Yeah, that would work. I don't think that it would be much faster, though, at least unless there's protocols I haven't seen to do that.
Okay.
Just as far as I know, the shuffle that we're using is the fastest technique to get what we're trying to do done.
Okay. More questions? Have a few more minutes? Yeah, a couple more minutes? Oh wait, someone new.
The hybrid version depends on the number of faults, right? So there could be executions in which the hybrid version actually takes more time. Is that right? Or did I misunderstand?
Yeah, the hybrid version can take more. So here, the descent plus verdict line, so the green line is the hybrid version. So if there is a disruption, the hybrid version takes slightly longer than the pure verify all the time version. And that's because in the hybrid version, again, participants are normally transmitting in this descent DC net. And when there's a disruption, they switch over to using the verdict DC net. So there's actually some time involved in doing that switch and then coming back. And so that's why on this graph, the hybrid version is slightly slower than the pure verdict version, which is the yellow line.
But if the hybrid version had like 3 or 4 descents, wouldn't that exacerbate the difference?
3 or 4 disruptions? Sure, but since disruptions are sort of exceptional events, I think basically what the hybrid DC net does is it trades off normal case performance for performance during a disruption. So once there's 3 or 4 disruptions, you'd hope that at least those guys aren't going to, that you've kicked out the disruptors and now you can continue on the normal case performance. So I guess, yeah, I mean, it does make it slightly slower when there's actually a disruption, but you assume that you've kicked out the disruptor after you've detected that person. So then you can switch back to using descent, and it's faster that way.
Okay, I'll take one more. So you do a lot of zero-knowledge proof checking in the lazy mode at the end, otherwise while you're going. Do you use batch checking for this?
Yeah, that's an optimization that we haven't implemented yet. So another optimization that I would love to look at is I saw work recently about like homomorphic zero-knowledge proofs, where you can actually, it's sort of like batch checking, but you can combine these proofs together and then check a bunch of them all at once. I guess that's like batch checking. Yeah, so that would be neat.